Okay, so there are many kinds of questions we can do in the acid-base section with a very limited amount of information. So the first lesson, you had to, we distinguished between an acid and base based on proton transfer. So you definitely have to figure out whether something's an acid or a base, and we'll look at a quantitative way you can do it today. And then you have to write conjugate acid-base pairs. We'll look at for sure, quantitative way you can figure out whether something's a weak acid or strong or base. Calculate pH, pOH, and OH. So on Friday, the 2 Fridays ago, we just did strong substances, which were a little bit easier. And then depending on if you have a base, you want to change it to pH, what the question asks, whatever, then you can convert between values. Today we're going to calculate percent ionization, and because we are going to focus on weak substances today, we are going to have to use ice. Okay, so the stronger the acid, the weaker its conjugate base. So that has to do with the fact that if you have a strong acid or base, the reaction is technically 100% forward. Which means that equilibrium is not established. It does not go in the reverse direction. So you get H plus, Cl minus. You can include water, and then you would write H3O plus, the hydronium. It doesn't really matter. The chlorine would be the conjugate base, the chloride ion. So, but technically, because it is 100% complete in the forward direction, it actually doesn't go reverse. So then, by saying the stronger the acid, the weaker its conjugate base, you're basically saying if it's a pure strong acid, 100% complete dissociation, the conjugate base is really useless. This chloride ion in this situation is not going to reaccept this proton to become the acid again. That's not going to happen. So when you have an acid, its strength is proportional to the number of hydrogen ions produced per mole of acid. So in grade 11, we talked about that a little bit, and looking at the fact that a log scale is not linear. It's jumps of 10. So a small increase in hydrogen ions can actually have a huge impact on pH, and the same thing with the base. Oh, there you go. A strong acid 100% dissociates. There's no HCl left. And then when you have something that's weak, it's only about 1% dissociated. So that means that we are going to have equilibrium established. And it says here, there is still mostly acetic acid molecules and some ions. Well, some's not good enough, right? We want to be more quantitative. So that's what the basis of today is. If you can't, or if the reaction is not 100% in the forward direction, we need to figure out how much is it going forward, is it going reverse, whatever. And the easiest way, what is at equilibrium, and the easiest way to do that quantitatively is with an ice table. So just as an aside, usually with organic acids, we write them like this. If you remember from the organic unit, that's what this is, right? The carboxyl group. And the reason we write it like this is to emphasize what proton is lost. So you don't have to really worry about that here. But again, if you continue in chemistry, you're going to want to make sure that when you have this kind of molecule, you're going to lose the proton because there's many here, right? Many hydrogens. So why doesn't it take one of these? Why do we write acetate like this? So it's implying that this one's lost because of the electronegativity difference here is much greater than it is here. So it's like the electronegativity of oxygen, it's sort of already naturally stealing the electrons from hydrogen's nucleus more often. So that makes this bond weak. So it makes more sense to lose this one. Sometimes people talk about it like it's the reactive site or whatever. So it's going to lose this proton. So usually with organic acids like acetic acid's common, formic acid or methanoic acid, which is 1 carbon instead of 2, then it's usually written like this. It doesn't really matter except that it's connected to which hydrogen is lost. So you wouldn't lose one of these, you lose this one. Okay, so when you have, when we're going to do ice, we're going to do equilibrium constants for the acid. So Ka, and for the base, so Kb. Okay, so if you have your textbook, there is a table of values. And when you have a strong acid, the textbook literally says very large. It does not even give a value for the equilibrium constant because it goes so far to the right. It is 100% complete in the forward direction. So then when you're actually given a value, so again, similar to the solubility section, you're probably going to be given scientific notation. Then that means that the acid is weaker and equilibrium is established, and you're going to do an ice table. So if you happen to do the homework from the other day, none of the questions gave you a Ka value. You didn't have to do ice. You could just sort of streamline stoichiometry and calculate pH very easily. Okay, so this relates to what we did with, is K greater than 1, equal to 1, less than 1? So and you can think of it mathematically. So as long as you remember it's products over reactants, then when the K value is less than 1, that means the reactant concentration is really big. What is the reactant concentration? Acid, right? So you have to sort of wrap your mind around that this is an acid, yes, but it's actually the presence of this molecule in a solution does not make something have a low pH. It's the presence of this. So if you have less hydrogen ions, your pH is not going to be very acidic, okay? So it's actually the hydrogen ion that is affecting the pH. And pH literally stands for the P is the power of the hydrogen ions. So if there are more hydrogen ions, then the pH is going to be more acidic and low. So then if you have a very low or very small Ka, then you have less ions, which means less acidic. So that is a quantitative way to decide whether something is a strong or substance. And similar to solubility equilibrium, ions are always the products. So the top of the fraction is very small, the bottom of the fraction is very big. What's at the bottom? Acid, the acid molecule together, not ions. so the solution is less acidic. So you can still use the principles from the very beginning of the equilibrium section. You just have to apply to this. Think about what the products are, think about what the reactants are. Okay, so the equilibrium constant is still going to be calculated products over reactants. You can add water as part of the dissociation equation, but because water is a liquid, we would cross it out. It's not included in the equilibrium law. Neither are solids, so plenty of you did not do that right on the quest. Okay, so no solids and liquids in the equilibrium law, so we're going to cross the water out. So all we are going to include are the aqueous substances. In this class, it'll always be 1-to-1. So the acid or the base will donate only one proton. If you have a polyprotic acid, like more than one hydrogen, then you still can do this math. It's just a little bit more involved. So again, that'll be for next year. An annoying part to the homework questions are good. However, if there is a possible Ka value, they're not going to give it to you in the question. They want you to go look it up, okay? So that's a little bit annoying. You also have to remember acetic acid is ethanoic and formic is methanoic. Sometimes your textbook loves short forms or common names, so you just want to jot that down. Just in the table, I forget if it gives the formula or not. When I'm going to give you a question similar to the solubility, the solids, like I'll always give you what the formula is. Like I'll write down CH3COOH, or so you'll know what acid it is, the formula. But I just can't remember what the chart looks like for sure compared to the question from the textbook. Okay, we can do the same thing for bases. Bases in general, weak bases are less common because they actually are pretty toxic. Things like ammonia, amines, those molecules are pretty smelly and sort of associated with the breakdown of proteins, which if you think about human beings, that's not really what we're aiming for, right? For example, when we talked about amines in organic chemistry, we talked about how the presence of an amine usually signifies decay of like an organic substance, like we produce cadaverine, putrescine, things like that when we start to decay. So if you happen to look at page 803, there's like a huge list of weak acids and then a tiny list of weak bases. Yes, we use ammonia, or ammonium nitrate, for example, is used in bombs. So obviously those substances are a little bit less, like you're obviously not going to put those on your French fries, right? So whereas weak bases or weak acids like vinegar, lots of times people will use acids in cleaning and things like that, putting in your pool, in your hot tub. And so, we use those things a lot more often. So there is a bigger list, okay? So Kb just is the base ionization constant. All the principles are the same. Strong bases are easier actually to pick out because they have OH in their formula. So if you look at page 803, there's actually not a list of strong bases like there is for acids because they're a little bit easier to pick out. But the same principle applies. The lower the concentration of ions that you're producing, then the Kb value is going to be going to be smaller, which indicates a weaker base. But really, just for practical considerations, we don't often ask you, we wouldn't, not that there's many theoretical questions to write answers to on the exam, but if this was normal and you had to talk about, you know, a weak acid or a strong acid, its conjugate base and that kind of thing, we usually focus more on acids because there are more acids in like that we use in the world. So the questions are just a little bit more practical. So you'll notice when you, if you choose to do the homework and you see the table in the back of the book, how many more acids are listed compared to bases. But you can do the same thing. So now it's still products over reactants. I've left water out of this equation. It's the conjugate acid, which has accepted a proton. So we write it like BH plus. And then it would have taken the proton from water. So what's left? The OH. And then the base concentration goes on the bottom. This one, again, these questions are sort of unique compared to other quantitative values. There's a lot of ways we can There's a lot of ways to convert between values. Kw is a constant. Which, if you need it, you would be given it. So again, because of the fact that water can accept and donate, it's amphoteric, then you can convert between acids and base values. But similar to pH, if a pH was low, that meant the pOH was high and vice versa. Then same thing here. If you have a big Kb or Ka, the Kb would be very small and vice versa. So sometimes the questions just ask you to do a whole bunch of calculations because it's pretty straightforward. You do the ICE table, you find out some value, and then you can do a lot of conversions with that value. Okay, so strong acids and strong bases completely dissociate into ions. The forward reaction is complete, so that means no ice. So all of the questions you should have done, whether it was the titration or the strong acid, strong base intro, none of them should have required ice. Weak acids and bases don't completely dissociate, so equilibrium is established, so we can do ice. So we're just going to focus, we're going to include strong acid-base even titrations, which is normal, like not even just in COVID, because if you had a weak base titrated with a strong substance, or strong or weak, it doesn't matter, then you would actually have to do ice and the neutralization stuff we did together. So the questions take a really long time, the math gets pretty involved, so we're just going to stick with the math we did last Friday and a very straightforward ICE table for this. Okay, so again, this is another formula that you would be given. You can do percent ionization, and a percent is the percent of something is how much is the part over the whole. So how many hydrogen ions are we getting in terms of concentration, usually per molar concentration of acid. You could use either ion. Like I said, we're gonna stick with 1-to-1, but because we focus so much on hydrogen and hydroxide in this section, usually that's what students will pick, but you could do it with the other one as well. Okay, so we're going to do now just a bunch of examples. On the exam, it is an acid, it's not a base. The last question is a base example, so just in case you need that again. Now, if you want to take a look at your note, I just noticed this, that I could have photocopied something different, but I didn't. So this one, you can write all here for the percent ionization. And then the next page is you can split it into 3 if you want, okay? So like the first example, the second example, the third example, it sort of prints weird when you leave blanks. So I think there's lots of space, basically, to put it there. If you do not like writing on paper with no lines and you want to use your own paper, that's totally fine too. So a student prepared a 0.1 molar acetic acid solution and found the pH was 2.96. Calculate the percent ionization. So in this question, this is a little bit weird because it doesn't give you a Ka value. So how can you know that that is a weak acid? Okay, so first of all, there's literally usually it's this one or formic acid. So if you choose to do really any of the homework, you'll get used to that as a weak acid. This pH is low, but it's not very low. It's not super low, okay? Also, if I asked you to calculate percent ionization for a hydrochloric acid, for example, a strong acid, all you would need to do is write down 100, right? There's no calculation involved, so that makes it a little bit simpler too. So if you want, you can write down some, background information in that space there. There's a lot of space for that question. So this question really is pretty straightforward. So you have to be able to write your own equilibrium equations, like your own dissociation. That is a thing. But if you can do conjugate acid-base pairs, that's basically what it is. So how do you know that CH3COH is a weak acid? pH is acidic, but not very acidic. You could look up the Ka value. It is a very common weak acid. So if you do any of the questions, then you'll just get used to it. So when you do this, you don't technically have to write the aqueous and the liquid. However, like I said, liquids are not included in the equilibrium law. So we are going to cross the water out. So sometimes chemists are lazy. Sometimes you'll see equations without the water. So then we're just going to donate the proton. It is acidic, so it is lower than 7. So that is obvious that it's acidic. And then water is going to accept. So technically, if you include the water, then what happens is this is going to accept and become H3O plus, hydronium. But remember, we use hydronium and hydrogen ions interchangeably. So if that bothers you and you'd rather not include the water because we're going to cross it out anyways, then you can just write this where the acid gives away an H. So on this side, you just get acetate and H. That's totally fine. Or, whoops. Technically, hold on, let me just fix that there. If you include the water, then you should technically write it as hydronium, but it really doesn't matter. So similar in the past, grade 11, if you were given grams, finding moles was an easy way to get marks. Changing for the first section of equilibrium, changing moles into concentration. So same thing here. Probably if you're given pH, you're going to need to change it into the H3O concentration. So as soon as you see the pH, if you want to do that, then that's a good way to get at least 1 mark. And the formula for that you're given, okay? So you just basically really have to know how to use log or inverse log on your calculator. So here's the pH. Whether you use H plus or H3O plus, it doesn't matter. If you prefer scientific notation, that's fine. If you don't want to use scientific notation, that's fine. You can use big M or moles per liter. Either of those is fine. So now we have the ion concentration, we have the acid concentration. If you don't like referring to acids as, like, I write it like this because A for acid with and it's going to be a hydrogen donor. You can write acid concentration. You can write out exactly what it is, the acid concentration. You could write this in brackets in the bottom. It doesn't matter. You would, if you needed this equation, you'd probably be given this form. Same with this. So you would have to adjust it, but and check the logic of your answer. Should it be a really low percentage? Yes, it's a weak acid. If it was strong, it would be 100, right? So that makes sense. Okay, so again, when you flip the page, so now I think you can use this whole top part, okay, for this example. Not that I think you're going to need it, it's just a nice table, but if you're a big writer, you can use that whole top part. Okay, so again, this is formic acid. This is literally one of 3 probably acids you would get. So a 0.1 molar solution of formic acid has a pH of 2.38. So before you even think about whether or not you need to do an ice table or not, whatever, if you want to change that pH into hydrogen ion concentration, that's probably a good first step, okay? But then it says find the equilibrium constant for the acid. So even if you did none of this work and you didn't know what formic acid was, you didn't recognize that it was written in that weird COOH way, which is literally like how every single weak acid is written, then the fact that you're asked to calculate the equilibrium constant means that it's not a strong substance. Strong acids and strong bases, their equilibrium constant is so large, we don't even give it a numerical value, okay? Or again, you could look at this. This is a low pH, but it's not super low, right? So There are plenty of ways to tell whether something is strong or weak. Or maybe you did the other homework and it's the reverse is true. The strong acid you're used to, HCl, HNO3, H2SO4. If you remember those, and then these ones are the weak acids, there's lots of ways that you can think about this, okay? So we are going to find the equilibrium constant. So if it's the equilibrium constant, then that means we need equilibrium values. So what are we going to do? We're going to do ice. Over here, I'm going to write some notes, okay? Okay, so for the equilibrium constant, similar to the first section of equilibrium, you had to plug in values that were from the E line of the ice table. So if you're asked to find the equilibrium constant, we need equilibrium values. And then you're given pH here. And so in the first section of equilibrium, it would say initially, blah, blah, this was the concentration. At equilibrium, blah, blah, this is the concentration. Then we did solubility. And all it said was the molar solubility is whatever. And you had to know, oh yes, okay, so molar solubility means the amount is a saturated solution. That goes at equilibrium. Same thing here. We're going to use the pH to find H plus or H3O plus if you prefer. And that value goes at equilibrium. It's essentially the same principle as solubility. You put the acid in, you give it a bit of time, it starts to dissociate, and the dissociation occurs when equilibrium has been established, okay? Okay, so the pH is going to be used to find the hydrogen ion concentration that goes in the equilibrium line. So we're really going to do two questions, one of them where you're given pH and one of them where you're not. And that's true of every single equilibrium ice table, really. Are you given X or do you have to find X? Are you given Ka? Depends what you're given. You also have to be able to write your own equation. So whether you think of it like acid-base proton transfer, or if you call it dissociation, or if you think about it like when you had to write conjugate acid-base pairs, all of those things mean the same thing. And again, it's up to you. You can leave out the water if you want and make it short formed, because chemists are lazy. Or you can write it with the water, knowing that water's a liquid, we're going to cross it out. It doesn't really matter. I'll give you the acid or the base. It literally says acid up there, okay? Also, the pH is lower than 7. That's how you know it's acidic. So acids are always proton donors. Again, technically, it's this hydrogen here that is donated because it's connected to the oxygen. If you took away this one, I wouldn't take marks off, okay? But just so you know. And then H3O plus. But we're going to cross out the water because it's a liquid, so if you prefer to be shorter, you can write that too. You'll get the same answer. It doesn't matter, okay? So we have some acid. We put it in water and we let it dissociate. So there's no ions to start with. So this should be always true in these questions, 0 and 0. So then you have to put the plus over here. This one goes down. So exactly the same as other questions. You either have information to give you the X value or you have the equilibrium constant. So in this case, we have the pH. So we're going to use that to find H3O plus. You could have done that first before you even did the ice table. It doesn't matter. It is concentration, so K, pH, pOH, KB, Ka, whatever. They do not have units, but concentration does. So please, that's an annoying mark to lose. Whether you like big M or moles per liter, make sure you include that. Or it doesn't have to be scientific notation. It doesn't matter. Whatever your calculator does is fine. Okay, so given the pH, it is going to be our X value. This is also X, so it's the same. And then this, we just subtract. Okay, so now we have E line, we have E equilibrium values, so we can calculate the equilibrium constant. Again, similar to the last section, you have to write it out. You can't just write products over reactants. You can't just plug the numbers in. You need to write the specific substances if you want to get full marks. So if you chose to just write H+, that's what you would put here. These are the same. You can write 4.16 times 10 to the negative 3 squared. You can write it out twice. You should get the same answer. You can check your logic of your answer. Is this a pretty small number? Yes. Okay, so then the chance of it being applied to the weak acid is pretty good. So the next example we're going to do is almost identical, except this time we'll be given the Ka value and we have to solve for the pH. So now we have acetic acid. Again, it's got that weird structure. It doesn't say acid this time, but you're asked for the Ka value, and A stands for acid. Okay, so maybe that's your clue. Okay, so we have 1, 0, it's virtually identical every single time. So when we did these kinds of questions in the solubility section, the KSP values were tiny, teeny, tiny, like 10 to the negative 9, 10 to the negative 10. So we used something called the 100 rule approximation, and where this number here had to be 2 decimal places bigger than this number here, or 100, right? So there are cases where I think that the approximation should not be used, but your textbook, like in order to get their answer, they still do. So yeah, it's really very liberally used here, and so go ahead. Make your life easier, because now we don't know anything at equilibrium. We're not given the pH. We're only given the Ka value. So if you plug this in like this, you're going to have to use the quadratic formula, which is fine if that's what you want to do, but we can use the approximation. So 1.0 is much bigger than Ka. How many times bigger? It has to be 100 times. So we can say 1.0 minus x is approximately equal to 1. I know it seems sort of, again, you know, there are times when your textbook will still use the approximation. I'm like, are you sure? But they do it anyways. So make your life easier, and when you have a value, you can ignore the x. These two have no values, so you can't put nothing, right? So you can't ignore those x's. Or put 1 minus x in the bottom, and then you would have an x squared term. You would have to make it into standard form and use the quadratic formula, or you can use this approximation. So this is 1, which is not going to affect anything, but really if something is dividing, then you would multiply both sides by 1 to cancel it out. And then you're left with x squared. So to get rid of the squared, you're going to square root. Because we're going to take this x value and go plug it into our ICE table, we're just going to ignore the negative root. We don't want that. You can't have a negative value. It's fine if you don't put units for x down here at the bottom, but make sure when you go to find the equilibrium concentrations that when you report it as equilibrium concentrations that you do include units. So it's up to you again if you were the kind of person who wrote it under your ICE table, what it was at equilibrium, that's fine. Or you know, you can write a sentence at the side. Lots of you did this too. These are both the same. They're both x. You can write it as scientific notation or not. That doesn't matter to me either. Just make sure when you're reporting it as concentration, you've either got moles per liter or big M, okay? So even here, you can kind of, you know, check your approximation. So really, especially if we were going to follow significant digit rules, then this, you would round to 1. So this concentration has hardly been affected at all by the dissociation, which makes sense. It's a weak acid. Usually with this kind of question, so this is where you would stop, you know, for the intro equilibrium section, solubility. But usually now, if you're asked to find the H3O plus concentration, then often you'll be asked to find pH as well. So that's just a simple formula. which you would be given. You just have to know how to use it in your calculator. And then again, kind of make sense of it. If it's a weak acid, then you should definitely get a pH lower than 7. Okay, so it's not a base on the exam, but we'll do one base one, okay? So now we have methylamine. So what happens with a base, they really basically all look like ammonia, okay? So a base is going to accept a proton. So say we had NH3, then it would make NH4 plus. It would gain an H, right? Ammonia and ammonium. So usually, especially in grade 11, we focus on that because you guys know what ammonia is. And you've heard of ammonium because it's a polyatomic ion. So the same sort of a principle applies to every base, okay? So if this is NH2, if it accepts a proton, then it will be NH3. Technically, because it gains a proton, it's going to gain a positive charge. Okay? But that's, yes, you should do that, but that's not super important necessarily. It's not going to screw you up. It's not going to screw up the math. But then you have to remember what else is going to be formed. So if water behaves like HOH, and the amine steals an H, then what's left? OH. So this is where Arrhenius was sort of wrong, right? So he said that bases had to have hydroxide ions in their formula. It had to dissociate to that, whereas weak bases they are basic. They will increase the pH of a solution because when they are put in water, they will accept a proton from water. So water is amphoteric, all that kind of stuff, okay? So now we have our ice table. So it's very, very, very similar. If this question asked for the pH, whenever you have a base, there's always an extra step where you have to do 14 minus pOH to get pH. But this question wants us to calculate the Kb. So we have to use the other piece of information we're given, which is the percent ionization. So similar to pH, and it makes sense, the percent ionization is how much ions you get, right? So where does that go? At equilibrium. So you can do that at the side. Both of these are X, both ions, OH and CH3, NH3+. So you can put either of those at the top of the fraction, but most people are used to thinking of bases with OH, so they'll choose OH, but it really doesn't matter because they're both X. So in fact, if you want, when you're solving an equation, if you would prefer to have X's as the unknown variable, then plug that in. So percent ionization, we're given as 6.3. OH is X. You can even put that there. The methylamine concentration is 0.1. But the problem is now, you just have to think about how you're going to solve this. Some people would automatically, whenever you're dealing with a percentage, divide the percent by 100. So you could do that as the first step. Like you wouldn't even think to write it down, you know? And then you just have to multiply by 0.1. And again, decide, do you like scientific notation or not? Because I don't care. This is concentration. So when you're given pH, percent ionization, something at equilibrium, that makes the question, I think, a little bit more straightforward. Okay, so then we're asked to find Kb. Some calculators are wacky, so you might have to do this times this or this squared, push equals, and then do the divide. Okay, and then it does say to do Ka. I just want to show you that. So again, that's this one where you would be given the formula, given Kw, you just have to plug in your value. And really, the annoying part to this is making sure that you can multiply and divide by scientific notation numbers in your calculator. So all you're going to do is do 1.1 times 10 to the negative 14 divided by 4.24 times 10 to the negative 4. Like this is our x, so you're isolating it. If this bugs you, you can change it into like standard notation. You don't have to use scientific. This is really straightforward. Just sometimes like actually typing it in can be annoying. This is a base. You do want to get a really small number for Ka. That makes sense.